Session sponsored by the Brosis Foundation. We're privileged to have these opportunities to share with you tips and knowledge in both English and math. Today, I'm going to start a new journey with you. I'm going to be discussing a concept that many students never get to see. It's called matrices. So we'll be diving into and trying to understand a beautiful concept known as matrices. So the first thing I would like to do is to give you an idea as to when is it useful to have matrices. You know, singular matrix, plural matrices. So let me just start by doing some vocabulary. Most people, the only time they've ever heard of matrix is the movie. But actually, there is a realm of mathematics that deals with matrices, and it's very useful in consolidating data and also in actual calculations, especially if you're trying to solve systems of equation. Matrices are also used in transformations. So there are many things that utilize matrices. So for now, I just want to go through some definitions and get that introduction in, and also give you a vision, give you an idea of how a matrix can be used, okay? Or how matrices can be used. So let's go through some discussion here. So singular is matrix, and plural is matrices, okay? So you'll hear me talk about a matrix, or you'll hear me talk about matrices having to do with plural, more than one, okay? So the question is, what is a matrix? I'm glad you asked. A matrix is really an array. It's a computer terminology. It's an array or an arrangement of data in rows and columns. Let me write that down, okay? So a matrix is so there's a new word. Let me put it like this so you can see. It's an array or arrangement of information in rows. And of course, rows are horizontal and columns. And of course, columns are vertical. So that's it. A matrix is an arrangement or an array, A-R-R-A-Y, of data or information in rows and columns, okay? For example, you could have a matrix that looks that's a matrix. Notice you have two rows, 3 columns. Got it? That's a matrix, right? It's an arrangement of data in rows and columns. There it is. That's a matrix right there. Okay? You must have the same number of items in each row and the same number of items in each column. Otherwise, it's not consistent. Okay? So if there's nothing there, then you put 0. Okay, for example, there's a space holder right here. Okay, so this, we'll talk about the size of a matrix. So let's continue in this discussion here. And you might wonder, when is something like this useful? I'm going to show you an example when it's useful. Suppose you're comparing school years. And you say, for example, these are boys, these are girls, and say 9th, 10th, 11th, and 12th. So if you saw here, say 300, no, let's use a smaller number. Okay, so now we look at what we have here. This row, the first row, deals with the number of 9th graders, male and female. The second row deals with the number of 10th graders, 11th graders, 12th graders. This column deals with the number of males, number of boys. This column deals with the number of girls. So that's a way that you could capture information in a very concise manner and gives you a lot of information very quickly. So, for example, suppose you're in a school district that has 7 schools, a few elementary schools, say 2 middle schools, and say 1 high school. Or say you have 7 schools, you might have, say, 3 elementary, 2 middle, and 2 high schools. Let's use that for example. You might have one of these matrices to show your student population at the different levels, okay? So you might be able to compare high school A with high school B, and you could see different trends and different things, so you could plan. Now for the middle schools, that will give you an idea how to plan for the high school. For the elementary schools, that will give you an idea how to plan for the middle school, etc., etc., etc. So this is a good way to do it, okay? If you want to infuse a little politics, you could talk about, say, for example, we had the 2000 and so this is so the 2020 election. We had the 2016 and the 2012, and you could have Republicans and Democrats. So in this, you could have the first row could give you the number of people voted Republican in 2020, 2016, 2012, number of people voted Democrat in the same time frame, and you could see if there is a trend. You could actually spot trends so you can make projections and make plans in strategic manner. So again, with a matrix, you're able to catch a very good glimpse, a good summary of significant information in a tabular form, okay? And then you could do different arithmetic with matrices. You could add, you could subtract, you could multiply, etc., etc., etc. We get there. So we're gonna be in matrices for quite a few weeks, okay? There's no rush. We're gonna take our time and explore this nicely. And after we're finished with matrices, we're gonna introduce set theory. So these are 2 terms that many people graduate from high school and even go into college and don't understand matrices or set theory. I'm going to spend some time to explore those 2 areas, okay? Good. So we have defined what a matrix is. Now we'll talk. So today is going to be a lot about definitions, and then we'll evolve. We'll get into doing arithmetic with matrices. etc., etc. But for now, we're just taking it slow. Okay? Size. So the size of a matrix. This talks about its dimensions. So when you speak of the dimensions of a matrix, what you're talking about is, you could say, for example, a n by m matrix. Or let's use two other letters to make it, say a p by q matrix. So the p is a number of rows. So the first number gives you the number of rows, and the q is a number of columns. So it's always row followed by column, row followed by column. For example, if you see this 2 by 5 matrix, that means you have 2 rows, 5 columns. How many items total? Well, the 2 times 5 gives you 10 items. Okay? This will be so this one has 6 rows, 4 columns. Okay? So now we have talked about the dimension or the size of a matrix is the number of rows followed by the number of columns. Okay, so let's talk about the information inside a matrix. So let's talk about the entries. We talk about the entries or elements. So those are the individual pieces of data within a matrix. So if you have a 2 by 6 matrix, then you have a total of 12 entries or 12 elements. Okay? And there is a notation, there is a way to specify a particular entry. I'm going to go through that definition for you. So, okay, if you have, say for example, matrix A equal to okay, so that tells me that A is a 3 by 4 matrix. A is a 3 by 4 matrix. So if I say to you, what is the A1 for entry? A, little a, so uppercase, you always name a matrix using an uppercase letter. It's always an uppercase letter. And then you refer to individual elements or individual entries using a lowercase. So when you have a lowercase with a subscript, so A, not 14, but A14, it's saying it's the entry in the first row, 4th column. Where is the first row? This is, let me use a different marker. So this is the first row, this is the second row, this is the third row. This is the first column, second column, third column, fourth column. So how do we find the A14 entry? We go to the first row and the fourth column. So first row, fourth column. Where do you have an intersection of the first row and the fourth column? The value is equal to 6. So the A14 entry is equal to 6. What about this one? A21. What is that? It's the item found at the intersection of the second row and first column. So that is the second row these are the items in the second row. These are the items in the first column. So the answer is 2. Let's try another one. A. So what is this? The entry, the A33 entry will be in the third row, third column. Third row, third column, that is 5. So far, so good? Okay, so let's have a little fun. Let's have a little fun. Oh, I could ask you, for example, what is the A42 entry? And you say, oh, fourth row, second column. We do have a second column, but there's no fourth row. So you say, not applicable, it does not exist. There's nothing. We do not have a fourth row. So you will find somebody trying to see if you understand the concept of an entry. They might give you one that does not exist and see if you will recognize that it's a trick, okay? Good. What we're gonna do, we're gonna do a little math using the entries. Okay. Okay, so we have 3 matrices. This is a 2 by 2. This is a 3 by 2. Notice 3 rows, 2 columns. And this one is a 2 by 4. Okay, 2 rows, 4 columns, 1, 2, 3, 4. So if I say evaluate, if I say to you evaluate A22 plus C, it's a little c, C31 minus D What am I asking you to do? I'm asking you to take the entry, the 2-2 entry in matrix A, add to it the 3-1 entry in matrix C, and subtract from it the 2-4 entry from matrix D. So go to the 2-2 entry, we see 8 plus C3-1, 3-1 is 9. Minus, 3 minus, what is D2-4? D2-4, so minus -2. So we see that the answer is trying to make space so it can fit. So it's 8 plus 9, 17, take away -2, so it's +2, gives you 19. Okay? Another example you could have is question 2, could say, what is 3C12 minus 5D two, 3. So now we're doing even extra stuff now. Instead of just taking an entry and doing stuff with it, we're going to actually have 3 times an entry. So what is this C12 entry? The C12 entry is -7. So it's equal to 3 times -7 minus 5 times, what is D23? D23 is 8. So it is actually -21 minus 40. It's equal to -21 minus 40 equal to -61. So we not only can find entries in a matrix, we can actually manipulate them. We can do arithmetic with those entries, as long as you know where to find what. And it's all about the naming convention. The first number is always the row, and the second number is always the column. Once you remember rows followed by columns, life becomes beautiful. Okay, so we have dealt with entries, and now we're going to go to something else. Okay. So for many of you, matrices is brand new. You have never done matrices before. So this is actually different. So far, pretty manageable, pretty easy, if I'm allowed to use that word, nothing complicated. But you have to know the protocol, you have to know the definitions. Okay? So here we go. Equivalence of matrices. Equivalence. If you are told if So if you have two matrices, A and B, matrix A, matrix B, and if ever you're told that matrix A is equal to matrix B, then there are two conclusions you must draw, and they're reasonable, they're logical. In order for this matrix to be equal to that matrix, they must be the same size. You can't have a small matrix and say that it's equal to a big matrix. It doesn't work. What does the same size mean? Must have the same number of rows in A and the same number of rows in B. There can be two different number of rows. Secondly, the same number of columns in A must be the same number of columns in B. That's why you have the same size. Okay? Next. Corresponding entries must be equal. Corresponding entries. In other words, the first entry in A must be equal to the first entry in B. The last entry in A must be equal to the last entry in B. Entries that occupy the same position in one matrix must be equal to the entry in the same position in the other matrix. So those are the two conditions that must be satisfied in order for two matrices to be equal. That's called the equivalence of matrices. So if ever you find out that there's one matrix that's equal to a certain number, but equal to a certain dimension, and you're told that it's equal to another matrix, you know that the other matrix has the same dimensions. Okay? So let's do an example how this can be appropriate. Okay? Examples. Okay. I just went all the way in to try and create confusion. That's what I do. I create rigor. I create confusion. So I can take a very simple concept and make it very complicated. So let's look at what we have here. We are told that this matrix is equal to that matrix. And as a result of that, they're asking you to find the value of each unknown. So I see the letter A, I see the letter B, I see the letter C, I see the letter D. Okay? So keep our fingers crossed and let's see what happens. Okay, good. So here we go. Are they the same size? Well, this is a 3 by 3 matrix. 3 rows. This is better. This is one entry. 3 columns. 1, 2, 3, 1, 2, 3. 1, 2, 3, 1, 2. So it's 3 by 3 also. So now what we need to do is we need to equate corresponding entries, and that's how we're going to solve. So this entry A is the 1, 3 entry. So this has to be equal to 15. So A is equal to 15. No big deal. Let's go to B. 3B minus 1 is equal to 3D. Uh-oh. That means we have 2 unknowns, B and D. So maybe we need to hold off on that particular equation right there. Let's work on the others first, and then we'll come back and see if we could fix that. So let's see, what else do we have? We have C. Negative 4 is equal to 2C. So you could write 2C equal to negative 4. Therefore, C is equal to negative 2. So we have 1, 2 things done. What about this? 0 is equal to this. So we could put 15 minus 3D is equal to 0. So therefore, negative 3D is equal to negative 15. So D is equal to 5. So now we know that D is 5. Okay? So now I think we can go back and solve this. So what do we have? We have 3B minus 1 is equal to 3D. 3B minus 1 is equal to 3D. What is D? D is 5. So I can put 3B minus 1 equal to 15. If D is 5, 3 times D is 15. So therefore, 3B is equal to 16. So therefore, B is equal to 16 over 3. So again, it's knowledge. Is that clear, Ronnie? Maybe I should just put it up here. B is equal to 16 over 3. So we have A is equal to 15, C is equal to negative 2, D is equal to 5, and B is equal to a mixed number, okay, or an improper fraction. Okay? So, how about matrices so far? So you see the concept, as long as you understand the rules of operation, then it becomes manageable. Okay? Let's do another one. Okay. So, what do we have? I'm going to write some crazy stuff out of my head. Crazy. So we have 2P plus 7, 3 minus 4R, 4 negative 3. Okay, I just went out of my way to make life miserable for all of us. I could have just written one letter, one number, and make it easy. No, that's too much. That's too easy. I like when we can process more complex concepts and still end up with the right answers, okay? So we have the letters P, Q, R, S, and T that we do not know. They are unknowns. So let's get to work. This is the first entry with a P, and we see a first entry here with a -1. So we can equate those two entries and solve. By the way, you see that this is a 3 by 4, 3 by 4. So that's good, it's legit, same size matrices. So 2P plus 7 equal to -1, which implies that 2P is equal to -8, therefore P is equal to -4. So one down, okay? But this entry here, we have a R, we also have a Q. So we're not gonna touch that yet, leave that alone. So what else do we have? We have a Q here and a -19. So I think we could work with that. So here we go. 5Q plus 1 equal to -19. So 5Q equal to -20. So Q is also equal to -4. So now we know Q as -4. So now we can actually find R because we know Q is -4. So we have 3 minus 4R is equal to -4 plus 2. All I did was, where I see Q, I put -4 plus 2. So now I have -4R equals to -2 minus 3. So therefore, R is equal to 5/4. So we have P, we have Q, we have R. So where is S? S is right here. 1/2 S is 20. So 1/2 S equal to 20. So therefore, I multiply both sides by 2, and I end up with S equal to 40. So we know that S is 40. Let's see, 40, yes, good. What else do we have? We have S, so now we have T. This is the expression for T, and we have -11 here. So we need a little space to work this out. Okay, so here we go. This is here, this is here. So -3 plus 4T over 3 equal to 16. Sorry, not 16, -11, sorry, -11. Equal to -11. So let's add 3 to both sides. We end up with 4T over 3 equal to -8. And now we need to get rid of the 4T, so we get T by itself. If I multiply both sides by 3/4, I end up with T equal to -8 times 3/4. So T equal to -6. So those are our answers. P is -4, Q is -4, R is 5/4, S is 40, and T is -6. So we have dealt properly with the inverse, not the inverse, or with the equivalent matrices or equivalence, matrix equivalence. So now we're going to go into some simpler stuff. Okay. There are two types of multiplications that are used in matrices. One is matrix multiplication, and the other is a scalar multiplication. So we're going to do the scalar multiplication. So the scalar multiple is where you just take the matrix and multiply it by a number. And the result is each entry in the matrix gets multiplied by that number. Example. If I ask you, so let's use number 1. 2 times 5, 8, negative 5, 6. And that is going to be equal to, the size doesn't change. The only thing that changes will be the value in each entry position. So 2 times 5 is 10, 2 times 8 is 16, 2 times negative 5 is negative 10, 2 times 6 is 12. That will be the answer. Let's try another one. Let's not use 15. So this one, we're multiplying our matrix by a fraction. The math does not change. We go through, we take each entry and multiply by this number. It's a scalar, okay? So now we end up with same size matrix. That is 7. That is negative 3. This is 0. This is 10. This is 4 over 3. And this is negative 2. All I've done, I've taken each entry and multiplied by 1/3. Multiply by 1/3, multiply by 1/3, all the way through. And that's our result. And one final one for this part is if I say negative 4 times, this time I'm multiplying by negative 4. And this is 2, negative 1, negative 1/2, and 3. So this time, instead of multiplying by a positive number, we are multiplying by a negative number. Result, we end up with, I hope by now you notice that the dimensions do not change. You got a 2 by 2 before, 2 by 2, you end up with a 2 by 2. 3 by 2, we end up with a 3 by 2. This again is 2 by 2, the result will be still a 2 by 2. So when we do the scalar multiplication, the size remains the same. So this becomes -8, this becomes 4, this becomes 2, this becomes 12. So the answer for this one will be -8, 4, 2, and 12. Okay? So we have introduced scalar multiplication, and now I'm going to give you a glimpse as to where we can go next. Okay? Okay, suppose you're looking at a school district that has, say, 3 elementary schools, 2 middle schools, and 2 high schools. So yeah, 7 schools altogether, spread out over an area. If you had, say, for example, school A, and you have first, second, third, fourth, fifth. Okay, so you are the superintendent of schools, and you're trying to make plans for the future. And these are your 3 elementary schools. 1, 2, 3. Suppose you wanted to find out how many first graders do you have in your school district. Then you could, how many boys and how many girls? If you add this and this and this, it will give you the total number of boys. Sorry, this and this and this will give you the total number of girls. This plus that will give you the total number of boys. So what you realize is that as long as the matrices are identical in size and also in data content, meaning that the entries, corresponding entries, relate to the same information, you can actually have a combined result. You can actually combine them to find out in your school district how many boys are in first grade, how many girls are in first grade, how many boys are in fourth grade, how many girls are in fourth grade, etc., etc. So from these three, you could combine them to get one matrix that gives you all the boys and girls in the entire district by grade level. So that's how useful it is in terms of creating a picture that gives you a good impression right away without having to read through the fine prints. Okay? So this is also excellent for comparison purposes. How does school 1 compare to school 2 in terms of the population in fourth grade? And you can compare this is this is that. So you can see what's happening, okay? And you can plan accordingly. So that is one of the big advantages of matrices. You're able to capture data in one compact format, and then later on, you realize that we're going to be able to manipulate the data by doing arithmetic with matrices. So that's where we're going to pick up the next time we get together, how to do different types of arithmetic with matrices, and then the fun will continue. On behalf of the Brosis Foundation, we just want to thank you for spending this time with us. Again, today we have spent time defining certain concepts regarding an area of mathematics which many students don't get to be exposed to. It comes under the category of matrices, and we spend time defining principles associated with matrices and also introducing some operations that we can perform. We're going to spend some time in matrices, maybe 3, 4, 5 sessions. We'll see at least 3 sessions. More than likely, it's going to be 4, 5, or 6. We'll see how much we get done. So this is where we're going to stop today. We just gave you an idea of what we need in terms of how it can be useful. If you are somebody who has multiple franchises of, say, Taco Bell, then you might want to capture key information per store in a matrix format, and then you can be able to get a quick glance as to how each store is performing compared to the others. Okay? So again, on behalf of the Brosis Foundation, we thank you for spending this time with us. We pray that you would tell a friend or a family about this great resource that's available, not only in math, but also in English. And we trust that you'll enjoy the rest of your day. Thank you so much.